Alright folks, so I was asked to go over one of these molecular geometry type questions. So here's a table from the practice exam that I gave you guys. Just basic questions. There's 4 different compounds asking you to draw the Lewis structure, how many areas of electron density are around that central atom, how many lone pairs are around that central atom, what are the bond angles then, and what the molecular geometry name is. And at the end of the test, I'll give you guys this table. This table is the one from the molecular geometry worksheet, so you don't have to memorize all this sort of stuff. You can just use this as a reference. So I wanted to show you how to approach a couple of these, and then I'll draw some of the structures on the bottom for question number 32. So let's start with the phosphine, the phosphor and hydrogen compound that we have here. If you're having trouble with the Lewis structures, I suggest that you go back and draw the Lewis structure of just like the atom. So just use the periodic table to determine how many valence electrons a atom has and do the trick that we talked about. So for phosphorus, since it has 5 valence electrons, you say, well, 1, 2, 3, 4, 5. So it looks like phosphorus should have 3 places for bonds, so it wants to bond to 3 different things, and 1 lone pair. And then hydrogen only has 1 electron, so here's yours 1. Hydrogen only wants to have 1 bond. So if you have 3 of those hydrogens, it looks like our Lewis structure should be something like this, where phosphorus has a lone pair on it and 3 bonds to hydrogen. That's a great Lewis structure. Shows us what it's attached to, how many electrons there are. And then when you go to the areas of electron density, phosphorus has 4 around it. It has 1 lone pair, 2 for this hydrogen, 3 for the next hydrogen, and 4 for the last hydrogen. So it has 4 total areas of electron density. Each of the bonds count, each of the lone pairs counts. So we have 1, 2, 3, 4. So there's 4 directions in which electrons are shooting off. In the number of lone pairs column, it's not the number of lone pairs in the total molecule, it's how many are on that central atom, so the one that's underlined here. So for phosphorus, it only has 1 lone pair, so it has 1. And then for these 2 columns here, the bond angles and the geometry name, you can just go to the table and use the information you just figured out. We just said that we had 4 areas of electron density, and 1 of them is a lone pair. So that must mean that the bond angles are around 109 and that my shape is trigonal pyramidal. Technically, you'll see in other books, it gets smaller. This is technically supposed to be a little less than 109, and that's a little smaller even. But around 109, that's totally fine by me. And I just need to take that, go back to the page where it asked about the bond angles, say it's 109 degrees, and say that it's trigonal pyramidal. So trigonal pyramidal. Does this have bond angles? Oh, sorry, we've got that extra L. Does it have polar bonds? Yeah, not very. But technically, it's not the same electronegativity. There's a small difference. And so this would be perfect score for this for the phosphine here. So all the information, we'll use that table that'll be in the back of your exam, and you can get all the information there. You don't have to memorize it. And I'll do a second one here. Let me do the last one, CO2, since it's a little different. Again, you could just draw the Lewis dot structure of the atom. This is for you. You won't be graded on this part, but carbon has 4 electrons around it, so 1, 2, 3, 4. And then oxygen has 1, 2, 3, 4, 5, 6 electrons around it, so it looks like carbon should have 4 bonds. Oxygen has places for 2 bonds. It has 2 unpaired electrons and 2 lone pairs. And so carbon dioxide should look something like this, where I have an oxygen double bonded to the carbon, and then another oxygen double bonded to the carbon. So that everything has an octet, everything has 8 electrons around it. All the lone pairs that are still there, carbon doesn't have any lone pairs, it wasn't supposed to. Oxygen has 2 lone pairs because it was supposed to. So this would be the correct Lewis structure for carbon dioxide. Now when we go over to the areas of electron density, this gets a little weirder because people are tempted to say that each individual bond means that that's an area of electron density, but it's more general than that. We're just saying in what area, what region do we have electrons shooting off. So as far as this carbon's concerned, it only has 2 areas in which electrons are shooting off from it. One is going towards one oxygen, the other is going towards the other oxygen. So this is really only 2 areas of electron density, or 2 electron clouds, you could say. So it's really only 2. We don't count each of these. We don't say that there's 4 bonds, so there's 4 areas of electron density. It's just that we have 1 direction shooting off with 1 oxygen, 1 direction shooting off with the other oxygen, so 2 total. There are no lone pairs on that central atom. Right? Again, I don't count the lone pairs that are on everything, just the central atom. There's nothing there. So again, I can go back to my little chart here. Here's two areas of electron density, so that means it's in the linear family. Your only option is that there are no lone pairs. So that must mean that I have bond angles of about 180, and this is a linear geometry. So I go back over here. Bond angles must be 180 degrees, and it's linear. Are carbon-oxygen bonds polar? Yes, they are always polar. There's a small difference in electronegativity. Oxygen is going to be pulling harder than carbon is going to be. So that's how you do number 28 and 31. So here's two examples. I won't go and do 29 and 30 also. I'll let you practice that on your own. Same idea though. Go through the same sorts of things. You use the table that's on the back of the exam or in your molecular geometries worksheet, and you can find it there. Now regarding the shape, draw the correct molecular shape. That's different than the Lewis structure, because the Lewis structure again just says, well, what is attached to what, and how many lone pairs are there. It doesn't say anything about the shape typically. The shape, though, we said that the phosphine is a trigonal pyramidal shape. That's a three-dimensional shape. That's in the tetrahedral family. So if I want to draw the correct shape for a phosphine, what I have to do is I need to draw the phosphorus. It has a lone pair on it. And then I'm going to draw one of the hydrogens with a straight line, because that means that this phosphorus-hydrogen bond is sort of in the plane of the computer or in the plane of your paper. And then we also have these dashes and wedges. Here I just drew a wedge. So here this phosphorus-hydrogen bond is a wedge. That's saying that this hydrogen is kind of coming out at us, that it's poking out of the computer screen, that it's coming out of the plane of the paper. And then we'll also draw a dash, which means this H is going back. H is going into the computer screen and going back into your paper. And so this is supposed to give you a three-dimensional drawing. It's supposed to give you sort of a three-dimensional shape here so that it looks like a pyramid. I don't know if that's the best pyramid in the world. It's supposed to look like a pyramid. It's supposed to be a trigonal pyramidal shape. It's supposed to be a three-dimensional shape here. Right? It's not a flat molecule. Even though our Lewis structure makes it look flat, it's not really flat. This is the correct shape, the trigonal pyramidal shape. And so when you draw these shapes, you want to make sure that you do these two things, that you include the lone pairs and you include any bond dipoles. People always forget this. Include lone pairs, include the bond dipoles. I already got the lone pairs. I already did that. There should be one lone pair on the phosphorus. But I didn't show any dipoles here. So phosphorus hydrogen is slightly polar, so I'll draw a dipole indicating that the phosphorus is going to get a little bit of the hydrogen's electron density. It's pulling on a little bit. So you can draw either of these dipole arrows, that's fine, or if you'd rather, if it's a little cleaner for you, you can draw the partial charges. I don't really care. They mean the same thing. They indicate the same sort of thing, right? All the hydrogens would be slightly positive, phosphorus would be slightly negative. So this would be a good drawing for one of the four. I'll do carbon dioxide also since I drew it up here. Again, this Lewis structure is perfectly fine. It looks a little funny because it has this little kink in it, and we just said it's supposed to be linear. So I just need to redraw CO2 as being linear. I'll draw that one over here in green just to be consistent here. I need to draw in more of a linear shape. So I need the carbon dioxide to have a linear molecular shape. So now the idea is that this is supposed to be more like the 180 degrees that we said it was supposed to be, right? This is supposed to be 180 degrees here. Just like all of these bond angles right here, this is supposed to be 109-ish degrees, about 109 or so. And so carbon dioxide, since it's linear, doesn't have any three-dimensional shape, so you don't need any dashes and wedges. It's really easy to draw. You just draw it in a straightish line. So if you put this as your shape for carbon dioxide, you get it wrong, because it's not a bent shape, it's a linear shape, because of valence electron pair repulsion, the VSEPR stuff. Did I include my lone pairs? Yep, I got 2 lone pairs on each oxygen. Did I include the bond dipoles? No, I did not, so I need to include that. So I have one dipole going towards one oxygen, one towards the other. Right? If you look at the CO bond, the oxygen's more electronegative, so it pulls electron towards it, which is why I have the arrow going towards the oxygen. And just like with the phosphine, you can draw either these bond dipole arrows, or you can just say, yeah, that oxygen's becoming partially negative, this carbon's becoming partially positive. That oxygen's becoming partially negative. That means the same thing. You don't have to do both. You can do one or the other. I don't really care. But these would be 2 great examples of how to do number 32, how to show the shape of the thing. So they should have roughly the angles that you said they should in that table, and you want to draw them in the right shape. You know, if it's linear, draw it linear. If it's a trigonal planar, draw something that just looks like the Mercedes-Benz emblem or something like that. If it's tetrahedral, draw a tetrahedral. If you have trouble drawing the three-dimensional things, don't pick one that has the three-dimensional drawings. Pick two of the easiest ones. It doesn't really matter. I just want you to have some sense that the Lewis structures do not tell you the shape of a molecule. They're just ways to represent what's attached to what. So here's how you'd approach this type of problem. I'll leave number 29 and 30 for you guys to practice, and please go ahead and email me if you have any more questions or post something on forums, and I'm happy to answer and work through more problems with you. Alright, I'll talk to you later. Bye.